We'll start with our first example of how to take an integer number, and then secondly we'll do a decimal number and convert them into binary form. Let's go to Microsoft Surface, and for integer, of course, we have to pick 42 as an example, as it's the answer to life, the universe, and everything. I don't know. You're probably a bigger Hitchhiker's Guide fan than I am. So for this, I do have my handy dandy calculation table that I made in Excel. You've probably seen that after watching the description of that section of the textbook already. So if we need to represent the number 42 in binary form, we need to at least go up to a digital value of 2 to the, it'll be less than 2 to the 6th for sure, because 2 to the 6th is 64. So remembering that actually 2 to the 0th counts as one bit. We have to count up from 0, 1, 2, 3, 4, 5, 6. So it's actually a count of 7 bits. I don't think we're going to use 2 to the 6th at all. It shouldn't be required until we get up to 100, much higher than 42. But in any case, we will lay out almost hangman style 7 bits just so we can demonstrate this setup. So starting with 42, what is the first value of 2 to the n that is smaller than 42? And that would be 2 to the 5th, which is actually 32. So we'll turn on the 5th bit. So that'd be 0th bit, 1, 2, 3, 4, 5, 6. So 2 to the 5th is 32. We'll switch that one on. And as I suspected, we didn't need the 6th bit whatsoever. 2 to the 6th is far too big. So that gives us a value of 32. We'll subtract that out of 42. This leaves, of course, a value of 10. The binary 2 to the nth power that is next, that is smaller than 10 but closest, is 2 to the 3rd, which is 8. So switch on the 3rd switch, subtract 8 out of what is left, and if we have 2, and at this point we have the exact match of 2 to the nth that matches the value of 2 we need. Of course, that is 2 to the 1st. So we'll switch that one on as well, subtract out 2, and we have the remainder of 0, which means this should be the exact and accurate, that's not a backwards 6, that's a 0, exact and accurate representation of 42. So if we were to go down here and say 2 to the 1st has a value of 2, of course we don't have any contribution from the 0th, the 2nd, the 4th, or the 6th. So 2 to the 3rd is 8, and 2 to the 5th is 32. If we add those together, we've already seen this actually sums up to 42. So that's one example, done and finished. Okay, to do a little bit more challenging transposition between a decimal and binary number, we'll do 10,127.4753. Maybe this is some data, it's just a random number. So the first thing we do, of course, is figure out what decimal value is the largest yet smaller than this number. And that'd be 2 to the 13th. Again, I don't have that memorized. I'm looking at a table right now on a separate monitor. And 2 to the 13th is 8,192. So because I don't know exactly how many decimal points it's going to take to get that trailing precision exact, I am just going to start from the left and keep adding blanks, essentially keep adding bits of information as needed until we obtain exactly 10,127.4753. So we started off with that value and we subtract out 8,192, which would be nice if the Surface would just do this math for me, but I'll have to click up here, 10,127.4753 minus. That leaves us with a value of 1,935, of course, 0.4793. 1935.4753. Okay, the decimal value smaller than that is now 2 to the 10th. So we see it from 2 to the 13th, 2 to the 12th is a 0, 2 to the 11th, 0, 2 to the 10th will be a 1. That gives us 1024. Yeah, come on. Leaving the decimal portion unchanged. This should be 911. Yes, I think I can math correctly. I'm just going to subtract that because I'm paranoid. Hey, I did math correctly. Congratulations. All right, so 911, we again just look in the chart. The bit smaller than that is now 2 to the 9th. Okay, right next door. So that'll be a 1 as well. We subtract off 2 to the 9th, which is actually a value of 512. For an end product of 399.4753. Run out of room fairly quickly, but I can fix this through the power of a better than analog whiteboard. I'll just drag things around. Okay, 2 to the 9th is 1. Let's see here, 399. The next one in the list smaller than that would be to the 8th. That is a value of 256. Subtract 256 off that number, leaving 143.4753. Okay, continuing the same trend, 2 to the 7th is 128. We're hitting ones on all of these. Leaving 15.4753. Okay, but we actually skip 2 to the 4th. Oh, we always skip 2 to the 6th, the 5th, and the 4th. I have to give myself some more room real quick again. By skipping those contributions, we enter them as 0 in the bits, because now 2 to the 3rd, yeah, 2 to the 4th, 16 is too big. So 2 to the 3rd would be 8. So that'll be a 1, so 15.4753 minus 8, and we just keep going on in this until we finally end up with a remainder of 0. And you can see this can take a while. This is going to be 7.4753. So that'd be 2 to the 3rd, 2 to the 2nd will be useful. That is, of course, 4. 3.4753. Well, did that a bit backwards. Everybody makes mistakes, no problem with that. Just be diligent and catch them. I have the advantage that if I make too big a mistake, I just delete the video and start over. Okay, 3.4753, 2 to the 1st. Of course, we have 2 to the 0th. We're almost down to that neutral value of 2 to the 0. So 2 to the 1st does fit at a value of 2. So 1.4753. And then 2 to the 0th is 1, which, of course, that would fit as well. My goodness, we're using all of the space. Okay. So we're now down to 0.4753, which is good because we're out of whole numbers. So we have a remainder of 0.4753, which is not big enough to fit 2 to the negative first value. In fact, I'll go over to the main screen again right here. You can see where I've been doing the subtraction, just line after line after line after line after line after line, subtracting off each value. And so we're down to 2 to the 0th, which is first. We now have to start accounting for all of these trailing bits. We have a remainder. That's the previous problem. Let me just finish up this. There we go. That's where we stand at the moment, 0.4753. So obviously 2 to the negative first is not going to fit, but 2 to the negative second will. So I'm just going to start keeping track here. Minus 0.25, 0.2253, yeah, so 2 to the negative third will also fit. Leaving a 10th left, 2 to the negative fourth will also fit. I can in fact just reference that value. 0.0378, just barely 2 to the negative fifth does fit. .00655. So that is a no. That is also a no. So 2 to the negative 8th is the next that will fit. So you can see you just chip away little by little by little by little until all the remainder is gone down to your level of desired precision. So we'll take that value, subtract off 00391. Yep, turning on that bit 002644. This one will fit. I wonder how far this is going to actually go. 3 zeros and a 691. 3 zeros and a 98 will not. 3 zeros and a 49 will. 3 zeros 2. It's a no. It's a yes. 4 zeros and an 8. This is getting quite ridiculous. You start to change the display precision of your Excel cells, you know it's gone probably far enough. Oh, I did not make it better. All of the precision. Good, none of the space. So 4 zeros and an 8. Oh, it's getting ridiculous. That's 4 zeros and a 6. That would actually fit. You can see our error here is getting very, very small. And this trend will just continue until technically you have nothing left. So actually this would be a 0 and a 1. That one would fit. At that point we're down to the millionths level of precision. So you could continue that trend until everything balances out, but you have to at some point with some of these irrational numbers that don't work out magically like some of the examples given in the book. You have to say that round off error is acceptable and just call it done. So if I can enter in starting from 2 to the 13th, these are the numbers that I kept on the surface. So it's 1 0 0 1 1 1 1 0 0 0 1 1 1 1 kill all humans 0. There we go. So that is the binary representation of 10,127.4753. Interestingly enough, you might imagine there's an easier way to go about this, and there is. So if we go to our handy dandy Google machine, type in decimal to binary. This is a handy tool right there. 10,127.4753. There we go. Hopefully we got the answer correct. Let's see. One 0 0 followed by 4 1s, 3 zeros, 4 1s. Yeah, hey, looks like we got it right. So then 0 1 1 1 1 0 1 1 0 1 0 1 1 0 1. Oh, is it really that close? Or is it? I wonder if it actually truncates to 0. I doubt it. I don't want to go 2 more steps. But you can see our process actually came up with the correct binary representation for that input. And you can do this with any length of decimal number you care to go about. So that is a more complex example of a truly complicated decimal to binary conversion.